Hi, and welcome to video notes on quadratic applications and a little bit of a mix mash on inequality. So we're going to really talk about two of things today, which is how does a quadratic function model real life, which is projectiles, and then we'll do a second topic on how it looks with inequalities, which is really more of an addendum because we've done that with linears in the previous units, and it's really the same thing except for it's a parabola as opposed to a regular line that we've seen before. So let's talk about this in terms of application. There are plenty of applications, but today we're going to get a little bit more specific with projectiles. This is anything from rockets to basketballs, any type of balls flying through the air, bullets, t-shirts, falling objects. T-shirt sounds weird, but that's where our example is going to fall. What we're going to do is get a very basic formula that's quadratic in its nature, and we just have to plug in a couple pieces of information, which is v, its initial velocity, how fast it's moving when it leaves the bat, the racket, the foot, whatever it is, if it's some type of ball that's played in a sports game. And also we need to know its initial height, which is the c here, about how far off the ground that it is when it's kicked. And again, this can be varied and changed, but this is the basic setup to kind of explain everything that's going on. What does that really look like? Well, if we think about anything flying through the air, we have to be cautious here because we're not actually tracking. If this is my worst foot I've ever drawn, it's not tracking the ball as it's motion through the air. And I keep using a ball because that's the easiest one to use. It's not tracking its distance versus time, tracking its height. So how far up does it go, and where can you find that in its path? So it's really just its height, not its distance. So don't think that this is the ball flying through the air. What does that look like with the quadratic? Well, we know that we've got intercepts, and we'll talk about those. But at some initial height, wherever that is, we're going to have a ball or a projectile, whatever it is, flying through the air. And so it's going to gain some height at some point because it was launched. And whatever that is, it's flying through there. It's going to reach its maximum height, which will always be its vertex. And again, these will all be downward facing parabolas, right? They're going to open down. So they'll be concave down or have an a value that's not greater or that's less than 1. Um, so that'll be the scenario here for almost all of them. You'll notice that that was a negative 16t. And then in that path of this parabola, again, height, not its distance, it will have a couple of our key features that we're going to talk about. Again, intercepts will make sense if they're inside of that application's how it fits, right? Don't forget your line of symmetry also in there. The vertex will be its maximum height always. The intercepts will be usually when it hits the ground. If it's in not a negative intercept, and a negative intercept is not in quadrant 1. Why do I bring that up? Because most of reality exists in quadrant 1. Only in special cases that we identify or make sense of does anything matter with negative height or negative time. Maybe that you're standing on a building and it falls past the building's top and that's where you launched it from. That might have a negative height. Negative time is rarely going to have any application for what we're doing. So this is what we're doing. We're sketching that height, that path of the ball, so that we can tell at any point in time on this trajectory, on this parabola, where its height is and at what time that occurred. So that's what that's going to give us. So without any further ado, let's go into a problem so we can see what that looks like. Now the one on the left here, you'll see on this side, I've gone ahead and done for you. It's very similar to the one that we're going to do, so reference it at any time. Make sure you write it down for your notes so that you have a couple examples to look back at. I did make one small change here just to kind of simplify the way the notes look. Make sure that you change that to launched. We're going to simplify this problem just a little bit. So you're at some type of a sporting event and they're launching t-shirts, which they commonly do. Everybody wants a free t-shirt, so get your hands up because they're shooting them or throwing them, however that is. In the example here, we're going to notice that we're launching at initial velocity, or this is our v, at 64 feet per second. And it's going to be launched from maybe the first row or first deck, not from the ground floor because we're 35 feet above the court, and that's where it's going to be launched from. So we have initial height or C value that's 35. Again, you don't have to memorize this. I'll give it to you for all our applications. So let's read the first question. Oh, before we do, notice that this one's a little bit faster from the same height so that you can do some compare and contrast on its vertex, because that's going to be some of the stuff we're going to find here. So it says, how long will it take the t-shirt to reach its maximum height? So my question to you is, what is this really asking us to find? Well, if we look at it, it's asking us to find the how long, or better yet, be careful with this, the time it takes to reach its maximum height. So it's not asking us for the height, even though it kind of looks that way. It's really asking us for what time that reaches. Well, how do we know where its maximum height is? Well, if we know it launches somewhere from 35 feet off the ground, that this is going to be a parabola facing downward, right? Because we know that that was a negative 16, plus all of these applications will have a negative a value. And so there's going to be some type of parabola to mark this transaction of this problem. And the maximum height is going to be achieved at this vertex, which is going to be somewhere on here. So there's going to be some maximum height, but that's not what it's asking. It's asking how long will that take? So really what we're looking at here is the x-coordinate of this vertex. So if we can identify this vertex, it's asking us to find the x-coordinate right now. So that's what our goal is. It's kind of actually important to understand what we're finding so we don't find everything and then piece it back together. We only need to find one thing, which is the x-coordinate of a vertex. Now we do have a couple approaches for this. We could complete the square or use b divided by 2a to put that in vertex form. And we could change it all the way to vertex form because the vertex is really what we're looking for in this problem. But I ask you, do we really need all of vertex form or do we just need that first coordinate? And if you're paying us extra special attention, you'll remember that negative b or opposite b over 2a finds our x-coordinate for our vertex. So this is going to give us our h value. In our line of symmetry as well, actually. We don't need it for that application, but that's what it's asking us to do. So let's go ahead and just use this because we're smart enough to know that that's all we need to find the time. So let's do opposite b over 2a, but first, let's write the actual application. So the function then would look like this. F of x equals negative 16t squared plus our initial velocity, which is 64 feet or times time, feet per second. And then we additionally have to add in our initial height, which is 35. There it is in standard form. It would be nice if it was in vertex form, but we never do that. We don't really write into vertex form too often, at least not from an application standpoint. And so we have this problem here. So all we really need for this piece then, instead of changing all the vertex forms, we just need that 64 feet per second. Now we're going to put it into opposite b over 2a, which is going to find our x-coordinate of our vertex. So 60 opposite 64 over twice times our a, which is 16, and that's going to go ahead and calculate to 2. So that's going to turn into 32, and it's going to be negative. I'm sorry, there's two negatives here, right? That should be a negative 16. I forgot my negative. So two negatives make a positive. So it's going to be positive 2 is what we're finding out. So what does that mean? Well, it's going to take 2 seconds to reach its maximum height. Okay, it's going to take 2 seconds to reach that maximum height. So we were being smart about this, and we understand enough about our parabolas, our quadratic functions, to know that we just needed to find that to answer that question. Without actually graphing, without changing its form, we're using the features of this to help us identify key information. All right, let's scroll down and do another problem then. It says, how far above the court level will it be? Again, what are we trying to find here? So if we go back to this one, it says this time it wants to know how high. And height was our y-axis. So this time we're actually trying to find the y-coordinate of the vertex. Well, if we've already got the x-coordinate and we've got the function, shouldn't we just evaluate the function at this x-coordinate, basically plug in x, and then find out what the y is? I think that would be the smartest way to go. Again, no graphing involved, no changing of forms. We're just going to go ahead and plug this in. So we're going to get negative 16 times 2 squared plus 64 times 2 plus 35. And let's go ahead and finish evaluating this then. So we're going to end up with negative 64 because 2 squared is 4, 4 times 16 is 64. And we're going to get 64 times 2, which is 128. And then we're going to have plus 35. Well, these are going to cut each other in half. So we're going to end up with 64 plus 35 here. And we're going to find out that this ends up at 99 feet in height. So how far above the court level does it get? It gets 99 feet in the air, or its maximum point is 99 feet in the air. And that's kind of understanding the situation and applying it. But let's look back at that other problem real quick. I know I haven't put that up here very much, but let's notice that this one had a little bit more velocity than the one that we're doing. Again, same starting height, but a little more velocity on this other problem. So look at how long it took to get to its maximum height, just a quarter of a second more. And look at its height here. It got a little bit higher in its trajectory, in its launch. So one last question though before we're done here. It says, what is the range of the function that models the height of the t-shirt over time? Well, let's think about that. So let's do a little sketch here. So we know that we found up to the vertex, but let's ask ourselves, what is domain? Well, domain is our x values. And if domains are x values, then we're really talking about time. So if we're looking at that, and we only found 2 seconds, so it might be tempting to put 2 seconds there, but that would be wrong. Because the range then is the flight overall, not just to the vertex, at least the way that I look at it. You could say 2 seconds if you wrote it out correctly, but I'd like to see that as its total path of flight would be where it could hit the ground. That would project everything that could happen in this scenario. And we could find all these other points of where somebody caught it or not, but we could talk about all of them if we changed our domain. So if we just doubled our domain, because if it took 2 seconds to go from here to here, then we know that it's going to take roughly 2 seconds to get down to the bottom. So 4 seconds of time total would be a good explanation. So if we look at the range, then the range is going to be the height. How tall did it get? So now we're looking at the y-axis. Well, it doesn't reach any higher from 0 when it could hit the ground, because we started at 35 feet, right, to that maximum height of 99. So its range, again, looking at y values, is going to be from 0 to 99. And that would reach every possible height that this t-shirt would fly. All right, let's flip over to the back side and we'll do some more there. Okay, so on the back side, what we're going to talk about is inequalities. And since we're pretty familiar with them, I'm not going to spend a ton of time going through them. Just remember this. They're the same as we did with linears. Nothing's different. So what that means to you is that if you have a less than or greater than, it's going to be a dashed line, right? The parabola will be dashed, so I'll do a little dashed curve. If it's got an equal sign underneath, then it's less than or equal to or greater than or equal to, and it'll be a solid line or a solid parabola shape. That part's pretty familiar. Additionally, what we're going to do when we graph this is that we have to shade. And if we're super smart, we've got two ways to do it. This is the second way, and this is the first way. Personally, in this one, I prefer the second way. Because if it's in standard form, having just a y on one side, if the y is greater than, meaning the solutions are greater than whatever the parabola happens to be. Doesn't really matter what it is. It means that we're shading above. The solutions are above the line. So if it's concave up, that would look like it's shaded inside. If it's concave down, it would look like it's shading above. And then vice versa, if we had less than or equal to, again, in standard form or vertex form where the y is over by itself, then we would shade below the parabola, meaning that it would shade underneath it if it was concave up, or if it was opening down, it would look like it's shade underneath it. So that's really all of it. The other point is, or the other way to do that is you can pick any point on either side of the parabola. So if you picked a point here, if that statement was true, which for this scenario it would be, you'd shade that side above the parabola. If you picked one on the inside, then if you happen to be true, then you would shade that one. If it was false, then you would shade the other side. So that would be by the test point. So either way is fine, but since the quickest way is if it's got y equals or less than or greater than or equal to, then we'll use that method. So let's scoot over here and let's graph this problem. Again, I've got one here. Go ahead and pause and write that down if you'd like to. I think it's a good idea. But let's do this one here and let's talk about graphing it. So if we were going to graph this, we'd try to find some information. Right now, it's in a very generic form. It's actually near its parent function, meaning it doesn't have a linear term and it doesn't have a constant. It's really basic in terms of a quadratic. Let's identify then. We can pretend that there was a linear term of 0x, and we could pretend that there was a constant. It would be 0. And we know from standard form that this is, or would be, I'll put a little plus minus in there, it really doesn't matter, your y-intercept. So our y-intercept happens to be for this one, 0, 0. Well, what's your angle or axis of symmetry? Well, axis of symmetry is just the x-coordinate of the vertex. So we would say x equals 0. So we've got two big pieces of information. Let's go ahead and graph those down. We know that the y-intercept is right here on the origin. And we also know that the axis of symmetry is also on the origin. So we got some good pieces of information here. So we've marked up our axis of symmetry, and we marked up our y-intercept. Let's go ahead and find the vertex. Now in the vertex, we're going to go ahead and do what we did before in the applications, opposite b over 2a. Well, b in this case is 0, so we've got opposite 0, which is really just 0, and then 2 times our 2, which is our a value, right here, -2 actually, right? -2. But isn't 0 divided by anything, even -4? Isn't that just 0? And it is. So our vertex and our y-intercept are the same. That just happens to be where it's at. So this ends up being our vertex, and our vertex then falls at 0, 0. Again, just making sense of the problem. Well, that's not enough to graph this, though, so now we're going to need to make a little table and graph some additional points here. So let's pick a point here, 1, and maybe a point here, and use symmetry to map them to the other side. So I'm going to graph 1. So we're going to take our function and evaluate it at 1, which is going to get us -2 times 1 squared, or 1 squared is 1, and 1 times -2 is -2. So there's our point, 1, -2. Let's plot that, 1 down 2. Does that make sense for everything we're doing? Sure, it's a negative value, so we know it's concave down or opening down. Great, that's working out just as we expect it to. Let's go ahead and plug in our second point here, which is 2. So we're going to evaluate the function at 2. So we're going to get -2 again times 2 squared, which is equal to 4 times -2, or -8. I think we got just enough room to do that. There's 2, 3, 4, 5, 6, 7. Well, 8's going to go a little off the page, so we should be at 2 and -8, which is going to be right about there. So we've got that half side done. We're going to use our axis of symmetry to map these points to the other side, equal distance from the same height. So we're going to scoot over a little bit here and put a point there. And that would be the -1 point we just found. So -1 and -2 is what that would work out to be. We're saving ourselves some work, right? And then again down here, we'll find at -2 that it's going to be -8 as well. So there's our symmetry point, which would be right about here. I think we got enough now to sketch this parabola out. So we'll go ahead and make a little line here and sketch the other side. So we've got a nice shape of our parabola. Now let's go back and look at the inequality portion. It does have an equal side. I was a little zealous and I already put that this was a solid line, but it worked out well because it is a solid line. And now let's talk about the shading. So this, remember, I like to say in my head, the solutions or the shading. The shading is above our, below our parabola. So below our parabola, if you go back to our notes, if it's open down, below would really look like inside. So we're going to go ahead and grab our highlighter, or you can grab whatever you have, and you're going to shade inside of here. And that's how you shade a quadratic. I did notice something as I was doing this. You may want to change this because this is not dashed. So I'm going to go ahead and fake dash this because it should be dashed because this does not have an equal sign underneath. So there you go. You've got two examples of inequalities and with parabolas. Again, same rules apply. Solid line if it's equal to, dashed line if it's not. Shade above or below based off of the y there, or use a test point if it's not in that particular form. Additionally, we talked about applications, which really means thinking about the features that we've talked about with a parabola and what we can find with them with the situation of any type of projectile. All right, thanks for watching today.